Welcome to our Further Mathematics series. Today, we will master first-order differential equations, covering exact solutions and integrating factors. Let us begin our lecture. Let's begin our lesson. This is a differential equation. It relates a function to its derivative, telling us that the rate of change equals 3x squared. Welcome to our lecture on differential equations. These equations model growing populations, they calculate the rate of cooling coffee, and describe moving vehicles, or even electric circuits. Let's look at order in calculus. Here is the first derivative, simply known as the first order. This is the second derivative, which is of the second order. And finally, the third order. Let's look at this differential equation. The degree is determined by this exponent. It's the power of the highest derivative, which makes this a second-degree equation. Ordinary differential equations involve derivatives with respect to a single variable. Partial differential equations involve derivatives with respect to multiple variables. Let's see how we can solve them. Let's start with our equation. We need to separate the variables. Notice how the terms slide smoothly to opposite sides. And now we can integrate both sides directly. Let's solve this differential equation by integrating both sides. This gives us the natural log of absolute y equals x squared plus our constant, c. First, we take the natural log of both sides. Exponentiating, we find our solution. And this is our general solution. Let's examine this standard form. Here, p of x and q of x are continuous. P of x is the coefficient of y, and q of x is on the right. This is a linear equation. Consider the integrating factor, animated as e to the integral of p of x dx. This function is key to solving our equation. Let's solve this linear differential equation by the integrating factor, which is e to the power of 2x. Now, recognize the left side as a product rule, giving us the derivative of e to the 2x times y. And that gives us our final general solution, y equals 3 plus c e to the negative 2x. This matches our initial condition perfectly. To model how populations grow, we use a simple differential equation. This equation shows that the growth rate is directly proportional to the current population. Let's examine how coffee cools. This process is described by Newton's law. The rate of change depends on the temperature difference. Notice how the graph approaches room temperature. Let's solve this differential equation. We are given an initial value where p of 0 equals 500. Applying the initial condition, we find our constant. This gives us our particular solution. Let's apply our population growth model. We will substitute the given values into our formula. This gives us 500 times e to the power of 2. Excellent work! You've learned the fundamentals of first-order differential equations. If you found this lesson helpful, please like, share, and subscribe to UNIC EDU for more undergraduate mathematics lessons.